Example 8.11. A 50 ohm transmission line is connected to a load impedance. Z load is given here. Okay. Then find the position and length of a short-circuited stub required to match the line. So let me try to draw the circuit so we can understand it better, hopefully. We have load impedance. Here it is given. And we have a short-circuited stub. Okay. The stub is connected in parallel. Also it is short-circuited. Okay. And find the position and length. So it is asking these distances D and L. Okay, so we need to find these D and L distances. For that, we need to find first of all normalized output impedance. Okay, Z out normalized Z load. So we can say. After that, we need to go. We can find admittance, normalized admittance. Okay, since the stub is connected in parallel, it is better to use admittance. Okay, so we need to find this one. After that, we need to go for admittance. After that, we can find these distances, but first of all, let's calculate these values. We know the output impedance here. To find normalized value, we need to divide by RO. This is RO. As you know, this value is characteristic impedance. RO I will write here. RO. I am using the touchpad. It has been a little hard. It is 50 ohm. So to find this, we need to divide these values here by RO. Let me divide 35 by 50. 35 divided by 50, it is 0.7. Okay, I am dividing it by 50 to find normalized load impedance. It is 0.7 and minus J again. If I divide this value 47.5 by 50, it is 0.95. 0.95. 95 ohm. Okay, we can find this point on the SWR circle on the Smith chart. Okay, let's say this is the center again, and if we rotate this arrow 180 degrees, so we will find normalized admittance, and this is normalized impedance. Okay, so to find this, let's find this point on the Smith chart, then we need to rotate it by 180. Okay, 0.7 minus j. 0.7 here, minus j. It is minus j, so we need to go down this circle, and 0.95. 95. So the intersection of these two lines here, this point, this is our ZL normalized. Okay, so let's take the arrow here. Yeah, it's fine. Also, let's find this SWR, standing wave ratio. The radius of the circle, which is this, 253. If we multiply this by 2, it is going to give us the diameter of the circle, SWR 253 multiplied by 2, 506. The diameter of the circle is 506, right? Yeah. Also, we need to center the circle. Now, as you can see, it is passing through this point. Now it's fine. Then, if we rotate this arrow 180 degrees, so it is going to give us the admittance. Let me duplicate this arrow, then take it on the other side. Here, if I go, yeah, this point, we need the lambda value, so it's better to go up, all the way up, okay, until you reach the lambda values. Yeah, it's fine. And this is our left, right. We don't need this point much, but it's better to write. This is our normalized admittance point, is here, the intersection. And we need this more, we need this lambda values, 0.11. Okay, so we have found this. Also, we need this 1 plus or minus JB circle. Okay, which is this one. It's coming, this circle is coming here, and we need to, let's draw this circle also. We need this, you will see why. Let's take an arrow at the bottom, arrow, you can say that we need this distance to draw the circle. So okay, and then also this needs to go to the center here, so it is going to give us the diameter, not radius. So if I choose this arrow for 9 6, okay, this circle 496, the radius of the circle here 496. So we got the diameter of the circle. Now we need to align it with this one. Okay, okay, yes. So this is the circle of 1 plus or minus JB, because the real value is always going to 1, this circle. Okay, so here it's always going to 1, and J values are changing, it is a variable. Okay, so this is the 1 plus or minus JB circle. Also this is our SWR. So the intersection point, we need these intersection points. Okay, let me write. I will, this first intersection point, I will call it as YD1, YD1, and the other one, it is YD2. The real values are always 1 for these points. It's going to 1 always. Let me write it here. YD1 and YD2 points. YD1 and YD2 points. Both of them, the real value has the same real value, 1. Okay, and the upside, YD1, it has plus J, and this one is minus J. And let's take a look at the J values here. Okay, this is YD1, both of them has the same real value, but the first one, it is plus J 1.2, plus J 1.2, and the other one minus J 1.2. If you don't believe, let's take a look. Where is it? Okay, here minus J 1.2. Okay, so we need these values to find the distances, D and L distances. Okay, so the D distance, this will be D1, this will bring us to D1. Also let me write D2. Okay, how to find the D distances on the Smith chart? So let's duplicate this. I will show you. Not that. Yeah, it's fine, we can do. Okay. Okay, this is in the center, and you are drawing this arrow from center, passing through the intersection points here. Okay, this is our first arrow. Okay, the first d distance is here, here to here. Okay, again from center, and this one, the intersection point of here. Okay, and the second d2, second distance for d value, this here, from this admittance value to here, this is the d1. Okay, and you keep going until this one, this is d2. So to find this distance, you can subtract this value from this one. Okay, this is 0.16 2 4 6 8. Okay, also we need to subtract this value here, 0.11. Zero point 11. Okay, this is d1. Okay, 0.58. Let me write here, d1 0.05. Lambda value. Okay, this is d1, and d2 is here until second intersection point of the circles, 0 3 3, and we need to subtract 0.11. Okay, same thing again. 2, 2, and 0. 22 lambda values. Okay, so these are the location values, position and length. Okay, position values, d values, two of them. And what about the L? Let me show you on the Smith chart how to find L value. Okay, so here it's coming here 1.2. Okay, plus or minus. We are trying to match the impedance. Okay, so we need to get rid of this 1.2 and minus 1.2. We need to cancel this. So here we need to add minus j 1.2, minus j 1.2. Let me do this. Wait. Okay, if we get rid of these imaginary values, so both of them will be 1 1, so we can match the impedances. So to get rid of here for y d1, to get rid of this imaginary part, we need this, right? Minus j 1.2, minus j 1.2, and plus j 1.2 for yd2. Okay, we need this points on the Smith chart. After that, I will show you here. Minus j 1.2 here. Okay. Then plus j 1.2 here. Again, we are drawing a circle here from center to these points. Yeah. Also, what about the lambda values? This one is 0.36 lambda, and the other one 0.14, the outer circle, outer values 0.14. Okay, we got this. Okay, now short circuit here, short circuit, we need to go from short circuit to these imaginary values. Okay, so if we are going towards generator, again we need to travel in the clockwise direction. It means, okay, from short circuit in the clockwise direction, short circuit to generator. Okay, the imaginary values are here. And what about the short circuit? We know the imaginary values, we know where we will reach. Okay, we will reach here, these points, two of them. But where to start and where is the short circuit? Of course, this here. The short circuit point is here for impedance. Okay, short circuit point. Okay, this one on the blue inner circle. Normally this was open circuit. If we were using the impedance, then this would be open circuit. But since we are using admittance, so this is short circuit because the stub is connected in parallel. So we are using admittance. So if we are using admittance, this point is short circuit point. So we need to travel from here to the imaginary points, imaginary values here. This 1.2 and here. Oh, again, let me draw with this distance L1 until this imaginary value. This is L1, okay? And if you keep going, full rotation after that, wait, full rotation after that this L2, this one, okay? So this is being L2, right? Plus L2, yeah. Plus J1.2 is L2. Let me write. Okay, this is L2. L2 distance. I will also call this L2 arrow, and this one is L1 arrow. And this one is D2, YD2, and this is D2. And this one is D1. Now, we are starting from the short circuit to this L1. So, the lambda value of short circuit, it is 0.25, okay? We are coming here to here, so we can subtract 0.25. So this is first distance for L values 1, 1, 0, 0.11. It is L1. L1 is equal to 0.11 lambda. L2 again from short circuit until the plus J 1.2 here. How to find this distance? Okay, we are making half rotation here. Okay, from here to here, half rotation, it is 0.25. Okay, 0.25. After that, we are coming here, L2, which is 0.40. So if we sum up these values, 0.25, it is half rotation. After that, we are coming to this point, 0.14. This is L2 value, 0.14. If we sum up 25, 9, 5 plus 4 it is 9, 2 plus 1 is 3, 0.39. Yes, 0.39. 0.39 lambda. And we have found two values. Okay, we are done with the problem, and most of the time we are taking the smaller value here. If we choose this one 0.11, then we need to choose, we are deciding according to L values, and most of the time we are taking the small distance. Okay, so also let's check the answers here. 0.11, 0.05, 0.058. Okay, so before I have taken these notes, the answers, okay, these are the answers we have found. Yeah, that's it for this video, I guess, and I hope you could understand, and I hope this was helpful. So thank you for watching. Have a good day.